In this example, we'll find all generators of the group Z10. Z10 consists of the numbers from 0 to 9, and the operation is addition mod 10. So the group is in additive notation. 0 is the neutral element, the unity, and the group is generated by 1, all multiples of 1. And you take all multiples of 1, you get the group Zn. And the order of 1 is 10, because 10 times 1 is 0. This is 10 mod 10, it is 0. So in Z10, 10 times 1 is 0. And this is the first time we get 0. So the order of 1 is 10. And 1 is a generator. Of Z10. To find the other generators, we use corollary 4 of theorem 4.2. It says that K K from Z10 is a generator if and only if the GCD of K and 10 is 1. So we go over the numbers in Z10 and determine when we get GCD 1. The GCD of 2 and 10 is 2. The GCD, so 2 is not a generator. The GCD of 3 and 10 is 1. So 3 is a generator. So this is the set of generators 1. Then we have 3. GCD of 4 and 10 is 2. So 4 is not a generator. GCD of 5 and 10 is 5. 5 is not. GCD of 6 and 10 is 2. 6 is not a generator. GCD of 7 and 10, they are relatively prime. So 7 is a generator. GCD of 8 and 10 is 2. 8 is not a generator. GCD of 9 and 10 is 1. So 9 is a generator. This way, we found all generators. There are 4 generators. And phi, the Euler function, phi of 10 is 4, the number of generators. Also, we can use this theorem 4.2 to determine the order of K. The order of K from Z10, so K is one of these numbers. K has order in Z10 equal to 10 divided by the GCD of 10 and k. The order of k is denoted this way, the order of k, the order of element in a group. So the order of k is this quotient. And we can find all orders because we found those GCDs. The order of k here, I can write it in this column. When the order of k, when k is 2, so in this column we have k. It is 2 here, 3 here. When k is 2, the GCD is 2. 10 divided by 2 is 5. The GCD here is 1. 10 divided by 1 is 10. That's why 3 is a generator. When k is 4, the GCD is 2. 10 divided by 2 is 5. 4 is not a generator. Any generator must have order 10. Here k is 5. The order of k will be 2. 10 divided by 5. 10 divided by 5. 6. 5. 7. The order of 7 is 1. 8. 5. And 9. 10. Here I made an error. 10 divided by 1 is 10. So we have 1 of order 10 and then 3, 7, and 9. 1, 3, 7, 9 are the only elements of order 10. And you see that this cyclic group of order 10, Z10, contains elements of orders 2, 5, and 10. Of course, it has an element of order 1. This is 0. 0, the neutral element, has order 1. So all these orders are divisors of the order of the group 10. And the subgroups of Z10 can be determined easily. Subgroups for each divisor, we get one subgroup of that order for each divisor of 10. Divisors of 10. These are 1, 2, 5, and 10. For each divisor, we have one subgroup of that order. Subgroups of Z10. Here we divide 10 by 1 and take the subgroup generated by that number. 10 by 1 is 10. 10 mod 10 is 0. We get the subgroup generated by 0, and it consists of the 0 only. 2, divisor 2. The subgroup generated by 10 divided by 2. 10 divided by 2 is 5, and all multiples of 5 in Z10 are this. 5, 2 times 5 is 10, and it is 0. So in this group generated by 5, we have only 2 numbers, so it is a group of order 2 as needed. How we get a subgroup of order 5? We take 10, divided this 10 by 5, we get 2, and then all multiples of 2, these are 0, 2, 4, 6, 8, and 10 mod 10 is 0, we already have 0. How many numbers here? 5. So this is subgroup of order 5. Subgroup of order 10, 10 divided by 10. This is how it is generated, but 10 divided by 10 is 1. And of course 1 generates the whole group Z10, all multiples of 1 are the numbers from 0 to 9. And the theorem says, the fundamental theorem for cyclic groups says, these are the only subgroups of Z10. Yes, if we take, for example, another element, if we take an element of order 5, like this 8, for example, 8 has order 5, 8 will generate a cyclic subgroup, like any element in a group. It consists of all multiples of 8, so 8, 2 times 8, 16, mod 10, we get 6. 3 times 8, 24, mod 10, it is 4. 4 times 8, 32, mod 10, it is 2. And 5 times 8, 40, mod 10, it is 0. So the group generated by 8 consists of these numbers from 0 to 8, but we already have that group over here. This is the same as this group that we already have, the group generated by 2. So an element of order 5 in Z10 will generate the same group Z2. So Z2 has 1, 2, 3, 4 generators.